Hello, so in this I'm going to be breaking down chemistry paper 1 for foundation. So all I'm going to do for this is I'm just going to go through each of the questions and talk you through my thought process when looking at these questions to break them down and simplify them so you can go through your answers from what you've done, and then you can understand why it is the answer and understand how you might get to that answer if you didn't manage to do it. So let's start. This question is about group 1 elements. As soon as it says group 1 elements, I am immediately thinking about the periodic table, which you are given in your exam. What are the group 1 elements known as? You only need to know the names of the three of the groups. The names that you needed to know are those three. And if you remember hopefully you've absorbed it through osmosis from your planner for long enough, that your group 1 is alkali metals, group 7 is your halogens, and group 0 is your noble gases. There's not really any other way of thinking about that you just got to kind of know what the group numbers are. So group 1 elements are alkali metals. Figure 1 shows a lithium atom. What is the number of electrons and neutrons in the atom of lithium? So it's talking about this specific atom of lithium. You don't even need to know the rules in terms of proton, electron, neutron, pen number or PNE, however you've done it. You just look at the picture and count them. So if we have a look, which ones are, for this one you need to know where the particles are in the atom. So if you remember, the outer ones are the electrons, and then the ones in the middle are the protons and neutrons. The protons are the positive ones. So the plus ones are protons, and then the dark ones are the neutrons. So then as long as you can remember that, we just count. So how many electrons have we got? 1, 2, 3. How many neutrons have we got? You count the dark spots. 1, 2, 3, 4. Be careful with that one, because yes, you would get 3 and 4 if you took the atom of lithium, because 7 take 3 is 4 for the neutrons. Sometimes it gives you a question where it's talking about this lithium atom specifically, so use the picture that they give to you for this. What is the relative charge of a lithium ion? So as soon as I see the word ion, I'm thinking loss or gain of electrons. We end up with a charge. And if you think about what lithium does, so lithium is in group 1. What do group 1 elements do when they are in a chemical reaction? They lose 1 electron, which an electron is negatively charged, isn't it? So if it loses a negatively charged electron, the overall charge will be +1. Question 1.4. Lithium is heated and then cooled in an experiment. So then you've got lithium solid, stage 1, to lithium liquid, stage 2, to lithium solid again. 2 physical changes happen in the experiment. If you think about physical changes, that's just talking about changes of state, where you can go one way and then you can come back the other way. So it's not a chemical change where we've got a permanent change. We're just talking about physical. Draw one line from each stage to the physical change that happens at that stage. So what state we're looking at, what is the physical change that happens at stage 1 and at stage 2. Be very careful with this, because especially people that are on foundation have a tendency to not read the question and then they'll draw more than one line. Draw one line. You can lose all of the marks by doing too many lines, just not reading the question carefully. So make sure you only draw one line. So first one, stage 1. What's happening? It's going from a solid to a liquid. What do you call that for stage 1? The answer is melting. And then for stage 2, it's talking about a liquid turning back into a solid. The answer is freezing. We know that because this one is not talking about state changes, dissolving, like dissolving salt in water. It's not a state change. Condensing is a gas back into liquid, and then boiling is liquid turning into a gas. So you just need to know your state changes for that one. Figure 2 represents the melting points of some group 1 elements. So we look at the graph, we've got a group 1 element, we've got 5 element names, and then the melting point up the side of the graph in degrees Celsius. 1.5, what is the melting point of cesium? So you've just got to read what the melting point of cesium is. The way you do that, you look at the graph, figure out what the scale is. So it's going up in tens, and if we have a look from 0, I always start from 0 and then go up to 10. So how many little jumps have you got? You've got 5 little jumps to get from 0 to 10. So that means each little tiny square is 2, goes up in 2. So if we look at cesium, so this is 20. I would always use a ruler for this, or draw. I wouldn't draw a line actually on this one because you're going to have to draw a bar chart, but if we had a ruler there, it would help us. So that's 20. So then the next little jump's 22, 24, 26. This would be 28. So the answer is 28. The melting point of potassium is 63 degrees Celsius. Draw a bar for the melting point of potassium. So I would just draw the top of the bar first. So we need to find, remember each little square jump is 2. So we're going to start at 60, which is here, and then 63. Well, if we go up one little square from there, it'll be 62, and then another little square will be 64. So 63 is going to be smack bang between, so it's going to be 1.5 little jumps. So we go from 60 and then we go 1.5 little jumps, draw a line with a ruler, and then finish off your bar. Obviously I can't use a ruler on this, but you'll be able to do a straight bar for yours. It's got to be 1.5 little squares above 60. For this, you are only allowed plus or minus half a small square. That's what the examiner is allowed to give you. So if you go any more than half of a small square away from what the actual correct answer, which is that, then you will lose the mark. So just don't be lazy with it, be very, very precise. Try and get it as exact as you possibly can. Describe the trend for the melting points of the group 1 elements in figure 2. So first off, we're describing, so therefore we don't actually need to say why, right? We don't need to say that. We're just saying what we see. So that's describing. We're not explaining for this, so you don't need to go in as much detail. And we need to be careful as well, because we are talking about melting points. So sometimes people get into the habit where they think about trend, group 1, they start talking about trend in reactivity. So they get more reactive as you go down the group because bigger atoms, etc., etc. So we're not talking about that. We're talking about the melting points, and we're just using this graph. So the first thing we can say is, if we look on your periodic table, the top element on group 1 is lithium, then sodium, potassium, rubidium, cesium. We're actually going down the group there. So the first thing we can say is, as you go down group 1, what's happening to the melting point? Well, lithium's was 180, then sodium's is 98, potassium's was 63 from before, which is there. Okay. And then rubidium's a bit less, and cesium's a bit less. So we can say melting point decreases. Now there's a clue that we've not quite finished the question for all of the marks, because it's out of 3. So we've got 2 of the marks there as the melting point's decreasing, 1 mark. As you go down the group, that's 2 marks. To get the 3rd mark, we need to make some kind of reference, because if you notice, it's not going down in a linear trend, is it? It's going down like a curve. So what we need to say is, we can say either or. We can say the initial drop is the biggest. So that just means the difference between lithium and sodium is the biggest, because sodium and potassium is not as different, and so on. Or we can say the difference is less each time. So each time we go down, the melting point is actually is decreasing, but it's decreasing by a smaller amount each time. And then we've got the boiling point of sodium is 883 degrees Celsius. What is the state of sodium at 150 degrees? So the way I would do that is I would draw the line the way you would do it, right? So you do a line and you put on the melting and the boiling point. So this would be our boiling point, so 883 degrees Celsius. So this is for sodium. This is the easiest way to do it. And then our melting point, which we can take from the graph for sodium, is 98. So this is our melt freeze point. This is our boil / condense point. And then we decide where on that line that temperature goes. So first off, if we have any temperature below 98 degrees, because it needs to be above 98 for it to melt, it's going to be a solid down here. If it's above anything above 883, that's above its boiling point, it would have turned into a gas. So anything between, it will be a liquid. So then we need to figure out where on this line does 150 go. 150 goes about there. So it's going to be a liquid. Figure 3 represents the electronic structure of a sodium atom and of a potassium atom. So we're still looking at periodic table. Electronic structure, we're talking about the rings and the X's, but it already kind of gives you that clue with the diagrams. So then it says, complete this sentence, choose the answer from the box. Potassium is more reactive than sodium because potassium more easily. When we're thinking about this, out of these three, don't just pick one randomly. So we need to think about what group are these in? What group? You can just look at periodic table, they're in group 1. Okay? And they are also, are they metals or non-metals? They are metals, right? We know that no matter what, metals lose electrons, okay? And we also know that if they lose, we know non-metals gain. The non-metals can either gain or share. And luckily we already know that these two elements are metals. So we're not talking about covalent already, we're not sharing electrons, and we just need to decide, is it going to lose or gain? But because it's a metal, we know that metals lose electrons no matter what. So potassium is more reactive than sodium because potassium more easily loses an electron. Just got to remember that metals lose and non-metals gain or share if it's covalent. This question is about hydrogen chloride and sodium hydroxide. First off, as soon as I see that hydrogen chloride, aka HCl, sodium hydroxide, that's first and foremost, I'm thinking, well, this is an acid, this is an alkali, which may become relevant later on in the question, but we can say that from straight off the bat, because hydroxide means alkali, and then HCl, hydrochloric acid, is obviously an acid. Chlorine atom has 7 electrons on the outer shell. It's being nice to you on this one because you're not even expected to find that for yourself. You should be able to do that because that's talking about groups, because it's in group 7. Hydrogen atom has 1 electron on the outer shell because even though it's not an alkali metal, on your periodic table it is. Most periodic tables it's in group 1 because it's got 1 electron in its outer shell. Figure 4 represents part of a dot and cross diagram for a molecule of hydrogen chloride. So dots, crosses and dots. Complete the dot cross diagram. And we're using those symbols to represent the electrons. You should only show the electrons in the outer shell. So if you struggle with this, what I would do first is I would just draw, for the outer shell for both of them, draw the initial electron structure. So for hydrogen is dead easy because hydrogen is just, we'll do hydrogen as dots because they've done chlorine as crosses. So hydrogen would just be that, and then chlorine is in group 7, so as crosses. Chlorine would be like that, 7. We need to think about what are these elements going to do. First off, they are both non-metals, which you should be able to tell from your periodic table. Chlorine is a non-metal. Hydrogen is the only one that's a bit weird because it's a gas, but it's a non-metal. Therefore, what do? They will share electrons because if it's both non-metals, what kind of bonding is it? It's covalent. Okay, we've been given the clue as well for the diagram that we need to do, because if it's ionic, that's the one with the brackets and the charges, but there's no brackets on there. It gives you the clue that it's not that one, so we know it's not going to be that. It's covalent. Then we decide what are these two elements going to do to react. How many electrons does this hydrogen need to gain? It needs to gain 1 electron. and the chlorine also needs to gain 1 electron. So what do? They share a pair of electrons in the middle, like that. So you always draw the shared pair first, and then you fill in the rest. How many electrons did chlorine start off with? 1, 2, 3, 4, 5, 6, 7 on its outer shell. How many X's have we drawn? 1, 2, 3, 4, 5, 6, 7. To finish it off like that. That's it. And you can always check. Hydrogen's got 2, that's the full shell because it's only got 1 shell. And chlorine should have 8 in total. 1, 2. Hold on, let me change colour. So 1, 2, 3, 4, 5, 6, 7, 8. Full shell. Done. Hydrogen chloride dissolves in water to produce hydrochloric acid. So HCl, hydrogen chloride. Hydrochloric acid reacts with sodium hydroxide solution. Now if you remember, before we said we've got acid here, because it gives you the clue in the question now. I mean, you might have done it from hydrogen chloride before, but now it's actually telling you that it's an acid. And in this one, sodium hydroxide means it is an alkali. So we've got an acid and an alkali. Complete the word equation for the reaction between hydrochloric acid and sodium hydroxide. So word equation. So what is the name? We don't need the chemical formula. Now the first thing to think about is if we have an acid plus an alkali, what do? If you think about, you take two ends of the pH scale and you smash them together, they end up in the middle. What's the middle bit called? It's called neutral, number 7, green. This is our neutralization reaction. And what chemical can you think of that is neutral? Well, the first thing we know is it's going to make water. And the other thing we're going to get, if you remember, is a metal acid salt. Okay, so depending on what the metal is that reacts in this, depends on what salt we're going to get, and the second part of the name depends on what the acid is. So the first part of our salt is going to be sodium. That's the first word. Second part, depending on the acid, what do we call the second part of the name of its hydrochloric acid? It's sodium chloride. If it was nitric acid, it would be nitrate. And if it was sulfuric acid, it would be sulfate. But it's hydrochloric acid, so it's sodium chloride. Solutions of hydrochloric acid and sodium hydroxide are reacted and the temperature change is recorded. In the reaction, we've got a mass of hydrogen chloride, a mass of sodium hydroxide reacting to make 1.8 grams of water, and we are going to calculate the mass of the other product. So first thing we're talking about when we're talking about mass, we're given a load of masses, we are thinking about conservation of mass, which simply put means the mass going in must equal the mass that comes out. So we figure out what the total mass of what is going in is, so we just add up the two reactants we've got to start with. So that's 3.65 plus 4 gives us 7.65 grams of reactants. So that means the products must equal a total of this number. So then we can just chuck in the numbers that we've got. So 7.65 equals, it's going to be the same, so we've got 1.8 plus something. Got to equal 7.65. So all we have to do is work out what the difference is. So we're going to do 7.65, take away 1.8, and you get 5.85. For the next one, figure 5 shows part of a thermometer used to measure the temperature. What temperature reading is on the thermometer? So remember, we're reading from the bottom upwards. We need to figure out what it's at. We need to figure out what each little jump is worth. So if we go from 16 to 17, we've got 1, 2, 3, 4, 5 jumps. So that means each little jump is worth 0.2. So then if we go from 17, we count it up. So we go 17, 17.2, 17.4, 17.6. Next question. In the reaction, the temperature increases. What type of reaction is happening when the temperature increases? So we're talking about thermic reactions because we're talking about temperature. And we've got two options for this because it's a thermic reaction. We've got exothermic, so heat exits the reaction, and we've got endothermic. So heat enters the reaction. And you've got to think about which one is which one is the one you feel as warm. Well, if his heat is being given out to the surroundings and leaving the reaction, then that means that is the one where heat is exiting the reaction. So for this one, it is exothermic. We know that as well because endothermic is the one where heat enters, it is absorbed by the reaction, so you would feel it as cold. So the temperature would decrease. So for this one, it's increasing, it's exothermic. Sodium hydroxide is an alkali. So we're thinking about the pH scale. Which two ions are in sodium hydroxide solution? So for this one, you've got to remember sodium is Na and hydroxide is OH, sodium hydroxide. The easy way to remember that as well is that that one makes OH minus ions in solution because it is an alkali, and then obviously an acid makes H plus ions, and obviously these two cancel each other out and you end up with neutral water. You should be able to figure out sodium is in group 1. Therefore, what does it do when it does a chemical reaction? It loses one electron. It forms sodium plus because an electron is negatively charged. So you've got sodium plus ions, and then we've got hydroxide. You should hopefully know is OH, the OH group, and there's only one OH there, so it's that one. Next question. This question is about structure and bonding. As soon as I see that, straight away I'm thinking about what are the 3 types of bonding. Ionic, covalent, metallic. Straight away. You can start thinking about what the properties are. Remember, ionic is a metal and non-metal. Covalent is non-metal, non-metal. And metallic is metal only. Figure 6 represents part of the structure of silicon dioxide. What type of structure is silicon dioxide? Well, you've got silicon and you've got oxygen. Okay, you just use your periodic table for this. What's silicon? Silicon is a non-metal. What's oxygen? Oxygen is a non-metal. So that already excludes, can't possibly be anything to do with metallic, anything to do with ionic. So we can already get rid of this one. The next thing we need to think about is either giant covalent or simple molecular, because covalent molecules can also be simple. Molecular just means a couple of atoms stuck together. So your example might be, is it just a couple of atoms like HOH, H2O, or, carbon dioxide, just a couple of atoms and then that's it? No, it's not. It's not simple. So it is a giant covalent, more specifically a giant covalent lattice. Each oxygen forms 2 bonds. What is the number of bonds formed by each silicon atom? So for this, you need to look at the diagram. Gives you the labels, tells you that these ones, so the light grey ones are oxygen and the dark grey ones are silicon. For this, it even gives you, because normally it cuts it off at the end, but it actually gives you the number of bonds from each one. You simply count the lines coming from each of the black circles, that's because it's all the same. So you just look at any one in particular. This one, 1, 2, 3, 4. Same again, 1, 2, 3, 4. And again, 1, 2, 3, 4. They're all 4. Figure 7 represents part of a fullerene. You should remember, hopefully, fullerenes are one of those carbon allotropes, covalent bonding, because it's non-metal and non-metal. Complete the sentence. The answer from the box, out of these words, the structure of fullerenes is based on. For that one, you've just got to simply use your eyes. Look at it. Look at the shapes that it's making. It's making this shape for all of them, and it's got 6 sides. Which shape is the one that's got 6 sides out of those on the box? It's hexagons. Next one, complete the sentence, choose an answer from the box. Fullerene molecule is shown. Figure 7 is made from, and we talked about this before, there's only a few things you need to talk about for the carbon. You just got to remember that you've got fullerenes, you've got diamond, and you've got graphite / graphene, all made out of carbon. Still talking about the fullerene. What is the fullerene molecule shown used for in figure 7? So For this one, we're not talking about, so what we need to remember for this is we're looking at how many bonds each carbon is making. So it's made out of carbon. This is the one where it's making 3 bonds and they are making hexagon rings. If we even drew that, that means if we draw the carbons linked together like this, making 3 bonds, what do we find? There is a delocalized electron. And what does that allow things to do? If the electrons are delocalized, it allows them to conduct electricity. So for this one, it is used for electronics. Figure 8 represents part of the structure of a polymer. So if you remember, a polymer is just if we take a simple chained thing, a monomer, and then we repeat it and repeat it again and again. Okay, so a polymer just means multiple repeating chain. What holds the atoms together in a polymer chain? Polymer is primarily made out of, well, 99.9% of polymers are made out of purely non-metals. And you're still thinking about bonding. Which bonding is only when you've got non-metals only, it is covalent. So it's covalent bonds. Complete the sentence, choose the answer from the box. So in figure 8, the polymer chains are held together by, for this one, you've just got to think about, we're talking about the chains, so we're talking about the forces in between the chains. Okay, so it can't be atomic because that's talking about individual atoms. We're thinking bigger than that. And for this one, hopefully, if we remember, we're talking about covalent, and one of the phrases you've always got to come back to for this one is weak intermolecular forces, always. So it's going to be intermolecular. And failing that, you should hopefully remember that whenever you're talking about anything to do with atoms, bonding and structure, this phrase macromolecular never comes up. That's never said in a lesson ever. So you should hopefully notice this one. Next one, figure 9 represents part of the structures of, so we've got a magnesium metal and then we've got a magnesium alloy. Soon as it says those words, so this one we're talking about pure magnesium, so that just means 100% magnesium, nothing else. And then an alloy is when we've got some different metals, different metal atoms. So that's a mixture of different metals to give us more suitable properties for whatever we're trying to do. We've got to calculate the percentage of copper atoms in the alloy. So the number of magnesium atoms in the alloy, you simply just have to count the number of magnesium atoms, which are the light grey ones. So we just count them. That's the first thing we need to do. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, 15, 16, 17, 18, 19, 20, 21, 22. We write it down. Number of copper atoms, 1, 2, 3. Total number in the alloy is, you add them both together. So that is 25. And then to get the percentage, we're trying to figure out what percentage of the total is taken up by the copper atoms. So you just do the number of copper atoms divided by the total and then times it by 100 to get it as a percentage. So we're going to do number of copper atoms is 3 divided by total number of atoms is 25 times by 100, and you would get 12%. 3.9. Explain why the magnesium alloy is harder than the magnesium metal. So to do this, we've got to look at the two pictures that we've got. If we take a magnesium metal, if we notice that all of the atoms are in nice rows, regular rows, in a regular pattern, in layers, therefore the magnesium, typical pure metals, are much more malleable because those layers of atoms are able to just slide past each other because they're all the same size. And then if we have a look at the alloy, we've got random placements of copper atoms in the total amount of magnesium atoms. So we've got different size atoms in that. So that's the first thing we can say for this one, is that you can specify. So we can say copper atoms are bigger than magnesium atoms, or you can say the reverse, magnesium atoms are smaller if you want. Then we also need to say, depending on the arrangement of it, and depending on the layers, depends on what the properties in terms of its hardness is going to be like. So what does that do to the arrangement of the layers if we put in different size atoms randomly in the structure? That means that the layers, there's a very important word you need to know for this one, are distorted. Gotta say, or disrupts. You could say disrupts the pattern. Something that means that. And then finally, because we're talking about 3 marks, so therefore we're going to have to say 3 things. Therefore, what can the layers not do in an alloy that they can do in a pure metal? Layers can't easily slide. Need that keyword, slide. This question is about elements and compounds. Immediately we're thinking about periodic table before we even start. Compounds, you're thinking about, you should hopefully remember what a compound is 2 or more different elements chemically combined. So then we look at the question. Magnesium and oxygen react to produce magnesium oxide. Balance the equation for the reaction. A lot of the time, if you really struggle with balancing equations, a lot of the time it will just be a 2, but we can also check. So the way we can do this, if we break this apart, we count the number of atoms on each side. So if I simplify this, I'll do it there, I'll just do it in a different colour. So if we have magnesiums and oxygens, how many are on the left side currently? We've got 1 magnesium. And how many oxygens? We've got 2. And then on the right side, because we've got a total of 2 of that overall, 2 of that molecule MgO, so we're going to have 2 magnesiums and we've got 2 oxygens. So then we look at this side, what do we need to do? So the oxygens are already balanced, so we don't need to do anything with them because the same going in and the same going out, right? The number of atoms in must equal the number of atoms coming out of the reaction, which is our conservation of mass. So then we look, how many magnesiums do we need to put into this reaction to balance the other side? We put 2. And then sometimes you would need to check it again, but we can change that now. So how many magnesiums have we got? We've got 2. Now it's all balanced. Sometimes you might have to go back and forth checking each side until you get it right. So just one safety precaution that should be taken when heating magnesium and oxygen. Most obvious one is wearing goggles. 99.9% of the time that will be the safety precaution, because you're protecting your eyes from any harsh chemicals. We could also say something along the lines of protecting ourselves from the heat, so we could say wear heat proof gloves. Okay, we could also say, if you think about what happens in terms of the chemical reaction of magnesium, we could say do not look directly at the magnesium because it goes really bright. And then the final one, calculate the relative formula mass for magnesium fluoride MgF2. So formula mass, I mean, you've already heard the phrase, we're thinking straight away, we're thinking relative atomic mass, which is on your periodic table. You should be able to figure that one out. So your relative atomic mass is the big number. The small number, remember, is the atomic proton number. But luckily, it's done us a favour and it's actually given us the relative atomic masses. All we've got to do is figure out what the total formula mass for MgF2 is. If you're struggling, draw out the atoms. So how many magnesium do we got? 1. How many fluorines have we got? 2. So then we just add up the totals. So we've got 24 for the magnesium, plus for the fluorines we need to do 2 times 19. Gives us a total of 62. Argon is a noble gas. As soon as it says that, group 0. Should be thinking, what group is it in the periodic table? Explain why no product is formed when magnesium and argon are held together. Well, remember, if we are talking about reactions, so chemical reactions, we are always talking about electrons. Something's happening with electrons when this happens. So there's an exchange, there's a sharing, something's going on. First off, if we draw the electron structure of argon, we should find that it is, I'm not going to do the full thing, but you've got 2 on the first shell, 8 on the second shell, 8 on the third. Okay, I'll just do the outer shell. How many can possibly go on that outer shell? 8 total. Therefore the shell is full. So for this, we can say argon has a full outer shell of electrons. Therefore, there's a keyword you could use. I'll just use the simple term for it. So therefore it is unreactive. That's your second mark. There's a keyword that means that. The word is inert. Argon is inert. It's got a full shell. Doesn't need to gain or lose any electrons. It's already stable as it is. So it won't react. 4.5, figure 10 shows the reactivity series. So we have our sequence of reactants. Immediately when I see that word, I'm thinking about, normally we're talking about displacement reactions. If we absolutely need to, we're talking about electrolysis. If we can't do displacement reactions, and we're thinking about whichever one is higher up the reactivity series will be able to displace the one that's below it. So obviously metal D could displace sodium, but not the other way around. Sodium could displace magnesium and replace it in a compound, but not the other way around. Draw one line. Don't know how many times I've seen people not reading this. You simply draw one line from each of the metals. You don't need to, just because there's 4 options doesn't mean you need to draw a line from each one. So draw one line from each metal to the method used to extract that metal. So basically to remove as the pure metal. Okay, so for example, extracting copper from copper sulfate rather than it being in a metal compound. So use figure 10. Let's look at metal D. So first normally we do this, unless you know it off the top of your head, do questions like this by process of elimination. So use the ones that you know that it's not to figure out which ones that it could be. So if we look at the bottom one first, removed from the earth as the metal itself, that's pretty much never happens, so it's not that one. Extracted from oxygen, from its oxide by reduction with hydrogen. If we look, metal D is much higher up the reactivity series than hydrogen, so we can't do that because it has to be, hydrogen would have to be more reactive than metal D to displace it, so it can't be that one. Extracted from its oxide with reduction from carbon, same again, carbon is below, it would have to be higher up to be able to displace metal D in a compound, so therefore for that one we're only left with extracted by electrolysis of a molten ionic compound, because nothing is in this is more reactive than metal D, so we can use electrolysis to split it apart using electricity. And then if we look at metal E, so we can do this the same again by process of elimination. Is it extracted from its oxide by reduction with hydrogen for metal E? Well, hydrogen is below metal E on the reactivity series, so that means hydrogen would have to be higher up for it to be able to displace it, so it can't be that one. So it must be the reduction with carbon. And we could check it because we know this because the carbon is higher up on the reactivity series than metal E, so carbon will be able to displace metal E in a compound. A substance conducts electricity when it has charged particles that are free to move. Right, there's a lot of information in that sentence if you know how to pull it apart. First off, conducts electricity, phrases that pop into mind. What needs to be able to be carried for something to conduct electricity? We're thinking about the word charge. What else could we be talking about? We could be talking about delocalized electrons. That would be if we are on about, so you've got still linking to bonding, so we're talking about potentially ionic bonding, we're talking about potentially covalent, we're talking about potentially metallic, all popping into my head from that first couple of words. We could also be talking, if we're talking about charge, we could be talking about ions. So first off, delocalized electrons only applies to metallic and those giant covalent lattice ones. And then we could be talking about ions carrying a charge. Then it says when it has charged particles that are free to move. So again, that doesn't narrow it down because that could be ions, that could also be electrons. Figure 11 represents the structure of sodium chloride. Now we're getting closer to something that we might actually be able to use. Sodium chloride, we should be able to figure that out pretty easily. Sodium is a metal and chlorine is a non-metal. Which one is it? If it's a metal and a non-metal, it's ionic. So this is an ionic substance. And we can see that because we've got the oppositely charged ions. Explain why sodium chloride, so we've got to say why. Explain why sodium chloride conducts electricity when molten but not when a solid. Very important, sometimes people lose marks. It's actually telling you that you need to talk about why not when a solid, not just why it will when it's a liquid. So first off, we need to figure out what are we talking about here. We've already decided that it's ionic bonding. So you get your first mark for literally saying the word ions. Because it's not said it in the question, means you've identified that we are talking about ions. And then to figure this out, you need to decide it already says it at the start, what do the particles need to be able to do to conduct electricity? They need to be able to they need to be free to move. When it's molten just means melted, therefore it's a liquid. Okay, so if you think about what the ions can do when they are in a liquid but they cannot do when they are solid, simple. So ions free to move when liquid, and then we just put the exact reverse, not free to move when solid. And that's pretty much your 3 marks. You could say they are fixed in solid, but it means the same thing. So mentioning ions, mentioning they can move in a liquid or when molten, mentioning that they can't when they're a solid. Figure 12 represents the structure of sodium metal. So we're talking about sodium metal, we're talking about metal plus metal, we're talking about metallic bonding. And straight away when you're thinking about metallic bonding, you're thinking about the metal ions, you're thinking about delocalized electrons floating throughout the structure. That gives us a hint as to what we might need to talk about afterwards. So explain why sodium metal conducts electricity when solid. Like we said before, possibilities of conducting electricity, we could be talking about ions, but that's only really when we're applying that to ionic bonding, which is not what we're talking about right now. We are talking about metallic bonding, and the other option is delocalized electrons. So first off, we're probably going to need to mention that in there somewhere. We know the 2 marks, so the first thing we can say is delocalized electrons. Okay, what does that even mean? All we need to do is say what that means. So therefore they are free to move and carry a charge. What I would add on to the end, just in case they don't want to give you all of the marks, depending on what it says in the mark scheme, you've got to say through the whole structure. You can't say throughout, just because they can't go anywhere they want. They've got to go in a specific direction depending on where the other electrons are, where the current is flowing. So you've got to say through. This question is about salts. So we've got green copper carbonate and sulfuric acid can be used to produce blue copper sulfate crystals. So we're talking about, we're thinking about crystallization already. Excess copper carbonate is added to the sulfuric acid. That just means too much. So that means we've got all of the acid has reacted and we've got excess copper carbonate left over. Give 3 observations you will make. Word observation means what you see. So you've just got to put 3 things what you see during this chemical reaction. There's quite a long list of what you could put. So we can start off, we can say what would this green copper carbonate look like? Most things going, well, 99.9% of things that you've reacted in chemistry are in powder form. So we can start off, we could say green powder, something that you would see. You could say what happens when you put the green powder in the acid. You would get some kind of fizzing effect. So fizzing because during the reaction. What does this look like? This is I'll do it in a different colour. This is a colourless solution. You could put that in there. Anything else? We could say, what does the solution, well, if the copper sulfate crystals are blue, what colour does the solution change when we do the chemical reaction? Solution turns blue. Okay. What else could we say? At the end of the reaction, we could say it stops fizzing. So they're 2 separate points that you could get for marks. We could also say if we've got our reactants, so these are our reactants, what happens when if we leave it long enough and they've fizzed and the acid has reacted, where have these gone? They've disappeared. So we can say the green copper carbonate crystals disappear. Okay, is there anything else? That's about it. You're just saying what you see. You're just literally saying, imagine the chemical reaction that's taking place. Just think about what would the reactants look like, describe it. What happens when the reaction is happening, describe it. What do you get at the end, describe it. You could say also, because we've got excess copper carbonate, you could say some green powder left at the end. And you only need 3 of any of those things that I've just said. You don't need all of that. But that's where the possible marks come from, any of those. So for this next question, there's 3 on this bit. So it says, how can the excess copper carbonate be removed? So you're thinking straight away, you've got excess copper carbonate, which means too much, means it's unreacted, and it says removed. You're thinking separating techniques, all of the separating techniques that we've talked about, right? So there's a list. What technique do you use to get rid of? Well, excess copper carbonate is an insoluble solid, which means it doesn't dissolve. What technique do you use to get rid of an insoluble solid from a solution? That technique is called filtration. Easy enough. Next one, the pH of the solution changes during the reaction. What is the pH of the solution at the end? First thing is talking about acid alkali, isn't it? Remember the pH scale, acid over to alkali, and your scale was numbers 1 to 14. So what number on that scale is it? Now, if you remember back to the previous question, I already told you that it was a neutralization reaction where we've got an alkali reacting with an acid, neutralizing each other. What number is neutral? What number is smack bang in the middle? It's 7. And then the last one, copper carbonate and sulfuric acid react to produce, we already talked about this, yeah? Alkali, acid, neutralization. Next one. So this one, it says ammonium nitrate is a salt. The graph shows the maximum mass of ammonium nitrate that will dissolve in 100 centimeters cubed of water at different temperatures. So one thing you may be aware of, your teacher may have told you, or you may just know this off the top of your head, if you heat up a liquid, the amount of salt that you can dissolve in it will increase. So you can try that at home, you can put a bit of salt in water and then make it warmer, you'll be able to dissolve more in it. Something to do. Along the bottom it says temperature. Along the side is the maximum mass of ammonium nitrate that will dissolve in the water at 100 centimeters cubed of water at whatever temperature it is. So it says they add ammonium nitrate to it at 80 degrees until no more dissolves. So this would be the maximum mass that dissolves. And then they cool the 100 centimeters cubed down from 80 degrees down to 20 degrees to produce crystals of ammonium nitrate. So you've got to determine what the mass of ammonium nitrate crystallizes out when they cool it from 80 to 20. So the first thing you need to figure out to do that is figure out how much ammonium nitrate will dissolve at 80 degrees Celsius. And that's where the graph comes in. So you can use your ruler for this, you can draw a line. I'm going to struggle to draw a perfectly straight line, but I can see it. So you go up to the line at 80 degrees, straightest line you've ever seen, and then you go across. So what it is it's actually 1.5 squares above from 80. So the first thing we need to figure out is how much is each little jump worth. The way we do that, if we look at 0, simplest way to do it, there are 5 little jumps from 0 to 10. So that means each little jump is worth 2. So if we're at 80 and we do 1.5 little jumps, that's going to be 3, right? So we write down first at 80 degrees Celsius, 83 grams dissolved. Right, one thing you can do on this one is there is a bit of a range for it. So if you misread the graph, you can have a range of somewhere between 82 to 84, but the correct number is 83. And then we do the same for at 20 degrees. So how much dissolved at 20 degrees? Go up to the line, and then we go across. So that's one little jump up from 30. So that's going to be 32 grams. So at 20 degrees Celsius, 32 grams dissolved. Now you can have a range for that one. You are allowed either 32 or 33. And then what we need to do is we work out how much crystallizes out when we cool it down, because not all of this 32 grams, not all of this 83 grams of the salt will be able to dissolve at 20 degrees Celsius. Only 32 will. So we need to figure out how much is left over that's going to crystallize. So to do that, we just calculate the difference. So 83 take away 32 gives you 51 grams. For this question, if you mess up these numbers and you do 82 and then you do 33 for the other one, as long as you did the maths correctly at the end, you can still get the third mark. So the maths has to be correct based on the numbers that you chose on your graph, but it has to be between these ranges of numbers. Next question. So this next question is about electrolysis. So the first thing I'm thinking when I see the word electrolysis is it's talking about the separating of something, splitting it up into its ions, positive and negative, go into each electrode. It talks about using potassium sulfate solution, so it gives you a hint as to what the ions would be that come out of that. And then it mentions inert electrodes, something to think about. Inert just means they are unreactive, so they are not a factor in this. It means that they'll last a long time. So then it says potassium sulfate contains K plus and SO4 2- ions. The only thing I'm really thinking about this is the charges on the ions. What is the formula for the potassium sulfate? If it's a formula, the overall charge of the compound would be 0. So they need to cancel out, because otherwise, as soon as it's got a charge, that means it would be an ion. So those two charges, the charges of the potassiums and the charges of the sulfate ions, must cancel out. So we're just doing some simple maths. So we're figuring out how many of those potassium, if it's just a plus, that's the same as it being a +1. So how many potassium +1s do I need to cancel out sulfate 2 minus. How many plus ones do I need to cancel out 2 minus? I need 2 potassiums. So I need 2 times potassium ions. And we just figure out which ones of these cancels out so that it's at 0 charge. I mean, we can test it. You'll figure it out, the answer, pretty quick, but I'll just do the first one to show you the method. So we've got, in this one, we've got 1 potassium, which would be overall +1 charge. And then we've got 1 sulfate group, sulfate ion, which would be 2 minus. That would cancel out to -1 overall charge. It's not that one, because if it's got a charge, it would be an ion. So let's try the next one. We've got 2 potassiums. That would be 2 plus. And then we've got sulfate ion, 2 minus overall. That cancels out to 0. So the answer, I mean, that's going to be the one. That's the one that cancels out the charges, but you can check it if you want to go through the method. The next one down, we have 1 potassium, so that's going to be a +1 overall charge, and then we have 2 sulfate ions, which would overall be 4 minus, or -4. That would cancel out to -3, so it can't be that one. And then the last one, 2 potassiums, +2 overall charge, and then 2 sulfate ions, which is -4 overall charge. That would cancel out to -2. So it's got to be the second one. This next question is still about the same electrolysis setup, so you're still using the same diagram. So it says figure 2, and bold writing, need to be using figure 2 to help us with this question in particular. Shows you the setup, shows you the measuring cylinders upside down, one with oxygen appearing in it as a gas and one with hydrogen. And it says, what are the volumes of gases collected in the electrolysis experiment? So the first thing we need to think about with this is you're talking about gas. So what people are going to end up doing with this most of the time is you're reading the volume of gas that's appearing in each measuring cylinder for oxygen and for hydrogen. And what people end up doing is they read it from the bottom and they think, oh yeah, I read a measuring cylinder. Normally when you fill it up from the tap, it goes up like a liquid does. But with this one, you have to think it's a gas being produced. You can see the bubbles forming. The bubbles would go up, rise up through the measuring cylinder, and then the measuring cylinder would actually fill from the top. So it's filling from the top down, and then it's pushing the solution out of the way. So you're looking at the measuring cylinder kind of upside down. It says the measuring cylinder is 50 measuring 50 centimeters cubed of volume. So the very bottom line is 50. And we need to figure out what these lines represent. So how many big jumps is it to get to 50? 1, 2, 3, 4, 5. That means each one on one of these jumps is 10 centimeters cubed. So obviously half of that is 5. So let's look at the hydrogen one. So we read it. I'll change the color for this one so you can see what I'm doing. So hydrogen, we're reading it from the top down. So we've got 10, 20, 30. So 30 centimeters cubed for hydrogen, and then for oxygen we've got 10, and then halfway to the next, so 15 centimeters cubed. It's pretty easy. It's just general measuring, using your ability to read measuring apparatus, but just understanding with this one, because you're producing gas and it's upside down, you've got to read it from the top. If you need to, turn your paper upside down and look at it that way. If you find it difficult to do it upside down, just turn your paper upside down. Makes it easy for you. So for this question, it says the student made the following hypothesis. It's like a prediction. The volumes of gases collected in this electrolysis experiment are the same ratio as hydrogen atoms to oxygen atoms in a water molecule. The first thing I'm thinking is ratio. What's a ratio? Ratios are the things that you'll have done in maths before, is things like 1 to 1, 2 to 1, 3 to 1, etc. And then you've got the key bit for this is it mentions a water molecule. I'm thinking, what's a water molecule? Well, a water molecule is H2O. That just means 2 hydrogens and 1 oxygen. And it says, explain how the volume of gases collected in the experiment. Figure 2, so the diagram earlier, supports the student's hypothesis. So use the answer that you did for question 0.02.2. So this is the volume of gases question that we did before. So if you remember correctly, I did volume of hydrogen was 30 centimeters cubed, and then the volume of oxygen was 15 centimeters cubed. So now if we have a look at, let's figure out what is the ratio of hydrogen to oxygen atoms in a water molecule. Well, it's 2 hydrogens to 1 oxygen, so the ratio is 2 to 1. And then the same, if we look at our volume of gases, if we put it as a ratio, 30 to 15, so 30 centimeters cubed of hydrogen to 15 of oxygen. If you simplify that down, that actually simplifies to 2 to 1. So you put ratio of hydrogen to oxygen is 2 to 1. You could even specify for volume of gases, and then so that's your first mark. Second mark, you just say for, so that is the same as the ratio in a water molecule. Now for this one, you can escape making a mistake for this one, because if you messed up the measurements of volume earlier, but you highlight that the ratio of water in hydrogen to oxygen in water is 2 to 1, but yours doesn't match that. So for example, let's say you did hydrogen was 31 and oxygen was, I don't know, 14. You could say the ratio is not 2 to 1, so it is different to the ratio in a water molecule. So you can get away with getting those marks even if you did not measure the volume earlier on. You just say the ratio is not 2 to 1, so it's different to water molecule. That's another answer that you could have done, but this is the correct answer. Next question. So this experiment was repeated 4 times. The volumes of oxygen collected in the 4 experiments are these following numbers. The mean volume that collected was 9 centimeters cubed. So mean, straight away I'm thinking what they've done there is they've done this plus this plus this, added them all together, divided by however many there are, which is 4. Then it says measure the uncertainty. The measure of uncertainty is the range of a set of measurements around the mean. So it's the range is the difference of how far away from the mean that it is. What is the measurement of uncertainty in these 4 experiments? So you find the mean. This is the mean, right? And then if we go up, so we're trying to find out how far is the range above and below from the mean for these measurements that we've got, right? The highest one we've got is 11, and the range of that is 2. That goes up by 2. And then if we go the other way, the lowest one is 6, and that goes down by 3. So you're picking the measurement of uncertainty is plus or minus, because the biggest one is actually 3. So it's going to be 9 plus or minus 3. So for this one, we've got 0.86 grams of potassium sulfate dissolved in a volume of water, 25 centimeters cubed. And it says calculate the mass of the salt needed to make 1 decimeter cubed of solution. So the first thing you need to highlight with this one, I'm thinking, is these 2 units are different. So the first thing you need to think about is, how do I convert that one of them into the other unit to make sure they're both the same before you can do anything further than that. So what you need to do is I would just turn centimeters cubed into decimeters cubed. Now, the thing that stumps everybody for this one is because it is cubed. So a decimeter is just 10 centimeters, but because we're talking about volume, it's going to be cubed that. So it's going to be 10 times 10 times 10, which is 1,000. So to convert 25 centimeters cubed into decimeters cubed, you need to divide by 1,000, which will give you 0.025 decimeters cubed. So what we've just worked out there is we've worked out that this much 0.86 grams of potassium sulfate is enough to make 0.025 decimeters cubed. So what you need to do then is figure out, well, what do I need to multiply this by to make it up to 1 decimeters cubed? So what you do is you simply do 1 decimeter divided by that number that we just worked out. How many times into 1 will this number go? So 0.025, 1 divided by 0.025 gives us 40. So that means if we want to make the solution up to 1 decimeter cubed, we're going to need 40 times more potassium sulfate. So all we need to do is do 40 times 0.86 gives us 34.4 grams. So for this one, it says plan an investigation to find the order of reactivity of the 3 metals. You should use a temperature change when each metal is reacted with the hydrochloric acid. Now for this one, it's talking about a method, so the first thing I would be thinking about for this is the variables. What are the variables in this? Because whenever we do science, things are changing all the time. We want an independent, so something we change, a measuring thing, so dependent variable, and then we want to control everything else, because otherwise our results mean nothing. So first thing I've highlighted is this, the 3 different metals is our independent variable. That is the thing we are changing. And then the order of reactivity is our dependent variable. And then there are going to be some controls in there, but we'll get to that later. So the first thing we need to think about with this is, what would a logical step be? Almost imagine yourself doing it when you're writing this out. Does it make sense if someone was to read this to actually follow this method? Because that's where the marks are going to come from. That's where you're going to get your 5 and 6 marks, is if someone follows this, does it actually make sense? Is it in a logical order? So the first thing I would do is, you're reacting with a metal and acid, right? You talk them through one of them. So measure a volume of acid, right? And pour it into a cup. I would even use polystyrene cup. Why? Because we're talking about temperature change. Polystyrene is an insulator, stop the temperature from changing too much, lose it to the surroundings to get a more accurate result. And what we would do is we need to work out the temperature change. How do we do that? We need to get the temperature at the start and the temperature at the end. So once we put the acid into the cup, we measure the starting temperature. Okay, then what we do is, when we want to get the reaction to start, we place a piece of metal in the cup, and then how do you stop the heat escaping even further? Put a lid on it. Right? So you just put the piece of metal in, let the reaction go, put the lid on to stop it from losing any excess heat to the surroundings. And then what do we need to do? How do we work out temperature change? We need to get the end temperature. So we wait until the reaction stops. So when reaction stops, measure the end temperature. Okay, and then calculate the temperature change, which is just the difference. Okay, once we've done that, we talked about what the independent variable is. So we've done that exact same method. So we just repeat the steps with different metals. And if we wanted to make it more accurate, this is where we're talking your 5, 6 marks. You repeat each one 3 times and calculate a mean. Then the next thing is, to really take it to the very, very top, is you need to talk about what are your control variables. So what are you going to keep the same to make sure that if someone followed this method, they would get 100% the best results that they could get from it. So what things you could control? You could have the same volume of acid. Must be volume, not amount. When we're talking about liquids, it's the volume of a liquid. Same concentration of the acid, because if it's more concentrated, that's going to make it go faster, so we don't want to change that. Same mass of the metal. Can't say amount, got to say mass because it's a solid. And you could also have the form that the metal is in, so that surface area, the metal being in a powder form or solid piece. I would just put same surface area of metal. You're just thinking for that, all I've done there is rattled off what are the things that might affect the rate of this reaction. I mean, you already talked about your concentration and surface area. That's just rates of reaction stuff, isn't it? And then the final mark is a conclusion. What conclusion can you make from this experiment? Well, how do you know which one is going to be the most reactive down to the least? It's going to be whichever metal has the biggest increase in temperature is going to be the most reactive. So metal with the highest temperature change is the most reactive. There you go. Try and imagine when you're doing these methods, if you were to go into a lab and do this yourself, logically what would the sequence of steps be? Because that's how you're going to scrape towards the 5 and 6 mark questions. Is it in a logical order for someone to follow it as a method rather than just putting a load of random bits down? Think about the order.